Hola.
Hola.
I modified the schedule a little bit, which I guess I can show somewhere. Okay, yeah, so I had this here at one point, but I moved it, so we'll actually have a class on the 23rd. And I added another homework, which I'm sure you'll love. But I wanted to divide up the molecular and the atomic. So you guys have this one, which is due in a couple of days, and then this one will just be a couple of questions on molecular stuff and dust. We need to figure out the second exam. And so I put this here originally, but it's super flexible. So I don't know if we want to do a doodle poll and have it similar to last time, or had on a Friday. It's completely, it could be a week later, doesn't matter to me at all. So it's mostly up to you, how you guys want to schedule things. There's a holiday on the 28th. There's, I think the university is giving a holiday to the undergrads on the 24th and 25th, Thursday and Friday. And so I moved this, I'm basically giving you the same holiday. And I moved this to the 29th, so it's not due on the 25th, for instance. And that way I can also have my office hours on the 29th, I guess, which is a Tuesday. And so you guys can ask questions if you need to before you can do that. Okay, but that also puts this very, very close to that. So that's kind of why I was thinking of pushing it back a bit, right? We still have time, we're right here. So give this some thought, and if you want to collectively tell me a day, that's great. If you want me to do a doodle poll, that's also fine. Okay.
I'm sorry. So it wouldn't be a problem if, for instance, you said it would be easier for us to do it like 1 week later, for example.
Like on July 4th or 5th or whatever it is. Yeah, that's fine.
Okay.
6th. I don't know what the calendar looks like, but
yeah. Yeah. Okay. Yeah. Okay. Then we're going to talk.
So there were these 2 days that were, I mean, they're officially still, we're part of the term, but we're going to finish early. So right, we could even go into the actual final exam week, the next week, and that's completely fine too. If you wanted 2 weeks off to study or whatever, you may also want to just get it done with and have a nice winter break. So I don't care. Okay, so that's that. I've been pushing Priscilla to get the homeworks done. She's struggling with something on problem set number 5, which is actually, she was supposed to deliver that back before the exam. Yeah. So anyway, the other thing is that these should all be graded and everything before this happens. I think I need to probably send out the answers to a couple of these, maybe all of them. I can't remember where I stopped, probably here. is where I stopped at problem set 8. I may not even send out problem set 7. So let me review that and send all these out soon. Yeah, so that should bring us up to current, I think. So we have 3 more classes effectively talking about molecular structure and then super complex molecular structure, aka dust. Yeah, any questions? No? Okay. Okay, and let's shift over to talking about, well, I wanted to finish this last sort of bit of atomic applications. And so let's just do that. This was kind of an interesting sidestep in that, you know, when we think about atomic studies, atomic lines and so forth, mostly we think about optical spectra, maybe going into the infrared a little bit. And so one thing that's sort of interesting is that when you have H2 regions, for instance, you know, they'll typically come into equilibrium. And so you'll be able to see recombination lines, which obviously the UV, the optical, the near infrared. You also see the continuum. You can also see recombination lines all the way into the radio. And here what we're talking about is like the transition from, in this case, this is H92 to H91. Right, so this is the 92nd level transitioning to the 91st level. So it's a very tiny energy change, which obviously comes out in the radio. And so you can see these. The benefit of going to the radio is that you don't have to suffer any extinction whatsoever. Right? So while this may be very strongly extinguished and you may have problems with resolution, here you can distinguish them pretty nicely. And so the other benefit is that the continuum that you get in the radio potentially could be due to Bremsstrahlung. And so you can relate the 2 properties, which are recombination, and then the Bremsstrahlung is the free electrons that are in this situation. And so if you make assumptions about things being in local thermodynamic equilibrium, you can pull out interesting constraints from this. And so this is just a little exercise in showing what can be done. And also you can, in fact, estimate when things are departing from LTE, which is interesting, which is not something you can necessarily do in the optical, but is something you can probe in the radio. And I'll show you why in a second. So basically this local thermodynamic equilibrium doesn't apply to all the recombination lines. So there are departures that are seen. And so if we think about how do we calculate rate of transfer in LTE, the absorption coefficient at the central frequency between these 2 electronic transitions will be given by this, right, by this formula, where this frequency is given by this. And so at radio frequencies, N is now very, very large. And then the energy here is typically much less than the electron energy. And the statistical weight is typically of order the same. There's not much change in the statistical weights anymore because it goes as N squared. So generally speaking, the spontaneous emission rate here will then just go as N to the 5. So it's a pretty strong factor of N. And then you can parameterize the line width as being something like this. So it's just based on this delta frequency. And so then the total number of atoms that are in the electric state will be proportional to this, right? So it's proportional to the densities, proportional to the ionization potential divided by the electron temperature, and then it goes as N squared here and has a temperature dependence, which is all what we sort of calculated before. So you can think about the total opacity of the line as being related to the number and then this absorption coefficient. Right? And so it's this combination of this full thing and then the line profile. And so combining all of these nice parameters together and noting that you have protons and electrons which are more or less equal, you get something which looks like this. So it goes as n squared, it goes as t to the 1 over t to the 5/2, and then the more line width, and a bunch of constants here. And so there's, what's interesting here is that there ends up being no explicit dependence on n, which we sort of pulled out of this. And so you have n squared here, you have n5 here, trying to remember where the extra n's are. Oh, let's see. Yeah, now I'm forgetting where there's a couple of extra n's here that come in. And okay, this is I think the fact that, oops, this thing. Okay. So generally speaking, this opacity or the optical depth can be translated to the emission measure and some frequency dependence and some temperature dependence. And so you can then turn this into a brightness temperature by just noting that the electron temperature times this optical depth is equal to the brightness temperature in this, as long as they're sort of optically thin. And in the case of radio, they should be more or less optically thin. And so then you multiply through this temperature, you get a small temperature dependence here. And then you can think about the ratio of the continuum to the ratio of the line in terms of its temperature. And so that ratio is given here. So this is the brightness temperature of the emission line. This is the brightness temperature of the continuum. And this is given by Bremsstrahlung. This is given by the line here. And so you can plug all those in and get a sort of functional form here. And you can also add in dependencies on, for instance, ionized helium versus hydrogen, if there is some ratio of the two. So with that, then you can think about how this thing will behave as a function of the electron temperature. And you can think about generally this line to continuum ratio will be an estimate of the electron temperature. And in fact, you have, because of this ratio, you get rid of the density dependence altogether, because both the continuum and the line emission depend on this emission measure. And so this ratio is simply dependent on the temperature, a little bit on the abundances and the width of the line, right, with a mild frequency dependence. So that's easy enough to do, and you can actually measure this for different ratios of n. And so this thing is nice because it's independent of this, as long as the frequency is high enough. So when you do this calculation, it turns out that this isn't exactly true, and there is a dependency on n. And that dependency comes from the fact that you're not in local thermodynamic equilibrium. And so this plot is showing as a function of the n level here. So 20, 40, so we were talking about things in the 90 region here. And so you have the fact that if you have local thermodynamic equilibrium, that ideally this thing could be set up by either collisional excitation and de-excitation or by photoionization. And so as you go between those two realms, you will have collisional de-excitation that kind of tends to steal photons away, right? And so you have an absorption that then doesn't have a photon coming away with it in the end. So that you have an absorption and then it never comes back. It goes into the collisional de-excitation. And so there's a parameter here, which is known as the departure coefficient. And so generally speaking, you have a sort of regime where radiative processes dominate. So this is photoionization. So this is pure photoionization. And this would be how the line ratios or the N levels would be sort of populated for photoionization. And then this is how they would be populated for collisional processes dominating. And this parameter here, this departure coefficient is the departure from this collisional ionization. And so you can see that as a function of density, you have a certain functional form for this collisional de-excitation. And this kind of mirrors what we talked about a couple of lectures ago about, you know, the cutoff level for the hydrogen atom is a function of the density, right? And so we calculated kind of what that would be for a particular density. And notice that cutoff level, we said, oh, well, maybe, you know, something like 100 might be decent for 10 to the 4. And you can kind of see that this thing asymptotes to this collisional process dominating around about 100. And as you go down in density, you can extend to larger radii. And so this is a function of density. And then also, I'm trying to remember what I think the dashed line may be for different temperature. I can't remember exactly what it was. So the point here is that by measuring a bunch of different N levels here, you can understand sort of what the density is of this, even though it's not explicitly in this, right? It's explicitly in individual in each one, but as a ratio here, it drops out. However, there's a mild dependence still. And so this allows you some extra flexibility in sort of understanding things that, you know, how the system might be in terms of its equilibrium state, and whether radiation is dominating or collision processes are dominating by just looking at the ratios of the different lines, right? And so this sort of temperature dependence of you can rewrite this temperature dependence as this ratio here. And so for recombination, you can say, okay, we have the continuum, we have this line, we can measure the temperature from it. As I said, you can also do this as a function of quantum number. And so this is what the Orion Nebula looks like. And so you can then map this into different regions. That's what they've done here. So they have a couple of different regions which are at different temperatures, which seem to make up the overall population. And these are not a huge range in temperature, about a factor of 2, different densities, different angular sizes, and then different physical sizes. And so you can kind of put together a picture of what the Orion Nebula looks like and how inhomogeneous it is. And these might be in sort of different pressure equilibrium. Right? So denser but lower temperature, and then hotter temperature but lower density. And so this is something you can sort of do to understand in much better detail the complex ionization processes. Any questions here? Okay. Let's see. If not, then let's dive into molecules. And so, much like we sort of had we have a question for the end of class. I got you. Okay. We'll start at the end of class. So, much like we had the atomic structure, and we had all of this complicated nomenclature. The nomenclature for molecular structure becomes even worse because it's much more complex, right? And so, if we take something like the simplest case is just a diatomic molecule, so hydrogen, is a diatomic molecule, 2 hydrogen with a molecular bond. And of course, hydrogen has a symmetric structure because it's 2 equal atoms, but you could have a diatomic molecule that has asymmetric structure like CO. And then you have a dipole there because you have asymmetric charge distribution, and this can be polar. So if you take a diatomic molecule, you have the Hamiltonian that you calculate for it. And this Hamiltonian is going to be, now, in addition to the motions of the electrons, you have the extra complexity, which are the fact that the nuclei are, there's not a static nucleus in the center now, but it's 2 nuclei. And those 2 nuclei are connected by a bond, and that bond can change. And so you have motion of the nuclei as well. And so the motion of the nuclei, right, the molecular size is typically about 1 angstrom in size. And so if you just think about Heisenberg's uncertainty principle, you have the fact that you can't locate the momentum and the charge to better than the Planck constant. And so if the charge is distributed on sort of the size of this molecular bond, so on the size of A, then this dictates that there's going to be a certain energy spacing here. And that energy spacing will be related to the uncertainty in the momentum squared, which you can sort of plug in here. And so this energy spacing will go as some constant divided by the molecular size, and then as a function of the mass. And so for electrons, right, if you plug in the electrons here, then they're going to have energy levels that are sort of the order of 1 eV. And then if you have the nuclei, there's obviously a factor of 2000 difference in mass, and so they're going to have energy levels that are of the order of sort of 0.1% or 0.001 eV, milli eV. And so to first order, we can kind of ignore the kinetic energy of the nuclei. So we assume the electrons are moving faster, the nuclei are more or less stationary. And then what we can do when we apply quantum mechanics and try to understand the Hamiltonian, we will calculate sort of order of magnitude computation of the energy levels here using the Born-Oppenheimer approximation, and the fact that the wave function can be split out into a nuclear component and a sort of global component for the electron distribution, where the electrons are shared between them. And so here we can compute this thing, assuming that this thing is more or less static or fixed, and then apply a perturbation from this to get out the corrections for this wave function. And so with that sort of in mind, we have these transitions of the electrons, which are going to be, the electronic transitions are going to be of the order of 1 eV. And so if these, a transition of 1 eV, it means it's going to be in the visual or the UV. And so the electronic transitions from molecules are typically seen in the UV or visual. And then we have the fact that the molecular bonds can vibrate, and those vibrations can take the form of sort of intermediate level. So we have the scales of 10 to the minus 3, which were sort of the rotational scales. And then we have the vibration scales, which are intermediate between the electronic and rotational, which have energies of sort of 0.01 to 0.1. So these are in the infrared. And then these with 10 to the minus 3 EV are sort of in the centimeter and millimeter band. And so to think about this in a little bit more detail, let's say we have a diatomic molecule, we have 2 masses, they're separated by some distance here, and so we have a center of mass if these are unequal, right? And so the center of mass will be related to this, and so you have some radius A, which is how far this thing is from the center of mass, and radius B, which is how far this thing is, and then the total distance. So in this case, we can kind of envision the states to exist sort of in energy and nuclear separation, kind of a little bit similar to how we had the atoms, but functionally it has a slightly different form. than the atoms. And in fact, when we have, recall that we had this more complex probability distribution of where the electron was going to be as a function of radius for the atom. And so here, this will be more complex, and you have spatial distributions as well when you factor in the spherical harmonic portion of the Hamiltonian or the wave function. But nonetheless, this is useful for visualization. So the idea here is you have differences in the electronic states, right? So you have a ground state, and the ground state has some probability in terms of where it's going to be in sort of internuclear separation. And then if you go up an electronic state, you have a big change in energy, right? From just the fact that we had sort of 1 eV changes. And so then on top of that, you have the vibrational states, which are these things. And so you can have higher vibrational states. And so they'll have, you know, more energy is bound in the molecule. Or you can have lower vibrational states. So it's lost that energy. And so it goes to a lower ground energy state. And then on top of that, on each vibrational state, you have rotational states. And so you have a very complex structure here that you have to provide nomenclature for to be able to specify the exact vibrational state and the exact ground state, or, you know, excited state of electronic state, and then the rotational state on top of that. Okay, so that's the sort of idea. Then you have more complexities, which are that you can have sort of combination vibrational rotational transitions. So you can go from, you know, a vibrational state here and a rotational state here down to a different one in the same electron state. And of course, there are selection rules about how you can transition between these. And then also note here this dissociation energy. And so at some nuclear separation, generally speaking, you'll have a dissociation. So there's an energy above which you can, you know, effectively dissociate this electron, or it'll just pop off and become ionized. Okay, so yep.
I have a question.
Sure.
How is the process to dump between the transitions? I mean, because I think that to dump between vibrational state to other transition is through photoionization or through collisions, or no?
No. So I mean, you can think of this, if you have a molecule in isolation, right? It will have, very similar to the atom in isolation, there's a certain probability that, you know, it will drop down to a lower energy state, and that those probabilities you can calculate them in the lab. And so, you know, we can assign, okay, there's a spontaneous emission coefficient with this particular transition to this particular, you know, this level to this level.
Mm-hmm.
Right. And so I'll show you I think maybe come back and ask me that question at the end if we haven't addressed it in sufficient detail.
Okay.
But it's coming. So yeah. But there's a lot of added complexity here is the problem. Okay, so this is just sort of a way of envisioning this. And so in terms of the nomenclature, you have different representations for what happens is the electrons, portions of them end up being shared between the atoms or the constituents of the molecule, and others which are sort of other levels which are kind of outside and more held by one or the other. And this is kind of trying to designate what this might look like. And so for the H2 molecule, right, the electrons are shared in between them. And so it looks like this or like this. And then sometimes you see it like this, where this is denoting 2 electrons here and the bond. You have diatomic oxygen, so oxygen 2, right? And here you have 4 electrons which are shared. So the inner 2 ones are sort of bound, and then the outer 2 ones, or the outer 4 here, are shared. And so it looks like you could represent it like this, or you could represent it like this with these 2 sets here. Likewise, you could show carbon monoxide. And so here you see that you have 3 sets of electrons which are shared between them. And you either have, you could either say asymmetries which could be represented. And then if you go to more complex situations, you might have something like this, which is the water molecule. So you have 2 electrons from this hydrogen, which are shared, 2 electrons from this hydrogen, which are shared. So it looks like that. Or you can represent it like this. And then you have ammonia, you have methane, and so forth. And so they potentially get a little bit simpler when you have very complex molecules. So they don't actually put all the electrons everywhere. And so, yeah. Okay, so that's in terms of nomenclature. You might see any versions of these. The basic building block here is the electronic states. And so molecules generally make less distinction, or no distinction between states, levels, and terms, whereas for atoms, it's a much more sort of rigorous nomenclature. And so the situation here ends up being very complex because each molecule generally has a very different orbital structure. And so it's not as easy to represent that as it would be for, going from hydrogen to helium. You have a nucleus and you have, just the shell, and you can kind of represent atoms with a similar structure. For molecules, you can't really do that because each one is sort of an individual snowflake. So diatomic molecules, generally, they are a little bit easier to do with because they sort of share some electrons between them, and then they have this extra structure here. So there's a variety of different diagrams you can show to indicate all of this complexity per molecule. Okay, so for diatomic molecules, you can classify the electron orbital angular momentum with just the internuclear axis because you have one single axis. And so you can generally break down the angular momentum that's along that axis and then the angular momentum that's perpendicular to it. And so this allows you a little bit of symmetry in the wave functions. And so you can have, something that has a phi symmetry. And so the wave function will go sort of like this. And then the wave function in the other 2 coordinates only depends on the angular momentum squared function. And so the electronic states are generally independent of the sign of m because they go as m squared. And so you can represent the different states as typically this lambda for electronic states, which is equal to the absolute value of m, which goes as 0, 1, 2, right? So you fill those states. And so this then describes this wave function here. And so typically the electronic states, which you could say 0, 1, 2, 3, these are called sigma, pi, delta, phi, etc. So they're Greek letters. And of course, they're not even in a clear, obvious sequence, right? So in this case, then, let's say we have these orbitals for the molecules. And in fact, there's a whole molecular orbital theory, which is denoted MO, typically, to kind of denote how these things will fill and what the tendencies are for which bonds would be the strongest, which one would be the weakest and break first, and so forth. And so if we think about an electron configuration for the diatomic oxygen, so dioxygen, we could write the electron configuration either this way, and so we have the lowest states here, and I'll get back to what these all mean in a second, but just we could write this as the first sort of the ground state would have sigma here, right? And you could then have, this ends up being a parity, whether you have G or U, and then you could have the second ground state, and then you could have the third ground state, then you could have sort of the equivalent of the atom would be the 1p state. So you could write it like this, or you could write it like this. And so these two are actually, these two are interchanged, and they basically just represent two degenerate orbitals here. And so there are a series of rules called Hund's rules, which allow you to understand exactly how things sort of fill and how the selection happens. And so basically from Hund's rule, if you have electrons which are in parallel spins in the ground state here, then this dioxygen is going to have a net magnetic moment. And so then it would be considered something called paramagnetic. So you can see already, just even with diatomic molecules, you get a lot more sort of nomenclature and complexities here, because you have these extra possibilities of having a net magnetic moment. You have different dipole structures that you can have. You can also have electronic configurations for what we call polyatomic molecules, so more than two. So see, carbon dioxide or H2O. And so these particular ones, they can basically change states without the absorption or emission of a photon in what's called a vibronic sort of change, which is a combination of vibrational and electronic term couplings. And so you can shift the energy sort of internally in a way that you don't have an absorption or emission of a photon. And then when you get to very, very complex molecules, basically solids, then the electron states become sort of extremely numerous. And in fact, they stop being discrete, and you start having sort of blending of these electron states amongst the structure of the solid. And these are known as electron bands. And then there's a whole entire subsection of physics called band theory, which sort of dictates how these things will behave. So this is just an example, a representation of the diatomic molecule CO. And so you have the ground, the individual carbon states here, the individual oxygen states here in terms of their energy levels. And then this is the combination of the CO molecule. And so what you can notice is that actually the ground state of CO has a lower energy level than the ground state of oxygen or the ground state of carbon. And in fact, several of these levels are lower than the ground state of carbon, or at least the 2s state. The 1s state's way down here. And so, yeah, you can basically compare these sort of levels and then the differences between them versus the individual levels of the atom. And so you can see kind of how they split out versus what the 2p state would be here. Okay, so we can start with the electronic states here. We can define what the state of the molecule is. And so here you can define an orbital angular momentum with a quantum number L. And so that's the total orbital angular momentum. And then you have to project a fraction of that onto the internuclear axis. And so that gives you the orbital angular momentum number, or the portion of it, ML. And so this ML is characterized by these quantum numbers, which are given in capital gamma, and capital gamma goes as 0, 1, 2, 3, and are then denoted by the capital versions of the letters I just assigned previously. Then you have a second parameter here, which is called multiplicity. And this deals with the quantum spin number, right? So you have a electronic spin angular momentum and a quantum number S related to this spin angular momentum. And so if we project that onto the internuclear axis, we have some value ms, or capital sigma, and capital sigma goes as 1/2, minus 1/2, 3/2, minus 3/2, etc. And then you have the coupling between the spin and the orbit. And so that's the total angular momentum. And so you have a total angular momentum number projected onto the internuclear axis, and that's given by this mj. And so all mj is equal to all ms plus all ml. Makes sense, hopefully. You can have positive and negative values of mj. And so because you can have pairs of positive L or S, and you can have negative L or S, and these are degenerate. And so typically the projection of this angular momentum onto the internuclear axis is denoted by the sigma, which equals this. And so then a given state will have a representation which looks like this. And so you have the main quantum number here, which is capital gamma, that's this thing here. Then you have the total orbital angular momentum projected onto, and these are all projected, right? So this is the projected version onto the internuclear axis. This is the total angular momentum. Then you have this is the 2s plus, so this is related to the total spin here. Then you have this thing, which is denoted as the Gerard or un-Gerard in German, but basically it's an even and odd parity term. And so it's kind of a symmetry term. But you'll often see a G or U here, or it'll just be left out if it doesn't really matter. And then finally you have up here a plus or minus, and this gives some idea of the reflection symmetry along the arbitrary plane of the internuclear axis. And so generally this is omitted when it doesn't matter. Occasionally you'll see it denoted as R or I instead of plus or minus, and this is regular or inverted. And so, yeah, unfortunately, all of these nomenclatures are possible and common, which is frustrating. So for a given state, okay, so let's say we had the gamma equals 1 state, and then we had sigma could be all of these potential spins. And so then you would be able to define those individual states as this one would denote this one would denote a second state, and so forth. So you would have these sort of combinations, which are the combination of the orbital angular momentum. This would be whether this is plus or minus 1, and then in combination with this. Ooh, that's quick. And so, yeah, so this would denote all of the sort of possible states here. Okay. And of course, not to be outdone, there's other notation, which you might see. And so just to explain it, the electronic states possibly can be identified by empirical single letter labels. And so typically X here will denote the ground state of this this electronic structure, and so this might then be appended by a G if it's due to it has even or odd parity, and so then you would have an extra term which would be the excited state of the same multiplicity, and this would be denoted by basically this would have the same spin orbital spin angular momentum, and then these could be labeled with successive letters. And then depending on how this could be either, if this was excited with a different multiplicity, then it would be in lower cases. And if it was with the same multiplicity, it would be in uppercase. So it ends up being very complex. And then the next set of symbols would then be the actual term that you would have for this particular state. So you can see it's all terribly complex. And then if you have polyatomic molecules rather than diatomic molecules, typically you add a tilde here to prevent confusion. And so something like CN would have an alternative label like this, where you've gotten rid of some of the things that you don't need or that you don't need to specify. The ground state of H2 might be given by this. So it's just extra terminology. It's all terribly complex and will hurt your head. But I figure I should tell you about it. So if you see it, you kind of know where to go look up how to interpret it. But I'm not going to ask you anything about this really. Okay. Any questions about this terminology? Mostly we're starting to dive into chemistry, right? This is, if you recall back to whenever you last took chemistry, you will start to see some of these things for these different transitions. Okay. No questions? Good. So then we can move on to a little bit more of the physics. And so here we then want to talk about the electronic states. And so the energy of the electronic state, if you're talking about molecular spectroscopy, you end up using a wave number, which is denoted by tilde frequency instead of energy. And so you have something, the energy, you have the frequency, you have the wavelength, and then you can also determine it based on HC, and then this thing is a wave number. And so you will often see that. And so typically you can express this energy in terms of a wave number and denote a term value here. And this, again, these terms are not the same as the atomic physics terms. And so an electric term value, so this is the energy in this particular term, will be related to some normalization, some sort of slope, and then it's related to the projections of the angular momentum of the orbital and the spin angular momentum along the internuclear axis. And so this gives you the sort of total energy of that particular electronic term. And then we can note that the spin has a fairly large influence on the energy here. And so the spin typically can change the energies in the atomic structure by of order EV. And so they are non-negligible. And so part of, you can have different orbitals that are occupied by sort of plus and plus or by plus and minus. And so that changes the overall energy dynamics of this. And so the parity or the evenness of a particular term is denoting, to some extent, what this spin is doing, whether it's positive or opposite. So you typically have the sign of A here is going to denote the parity of this particular term. And so if A is greater than 0, you have a regular multiplet. If A is less than 0, you have an inverted multiplet. And so this is where the plus or minus comes in, or the R or I designation in the nomenclature. So then we can think about how this will actually work in practice. And so when we talked about an atom, we used a quantum harmonic oscillator to give us some insight into where in space the electron would sit, right? And so with molecules, you don't get a very good approximation by using the quantum harmonic oscillator, but instead you get a better approximation by using something called a Morse potential, which is this blue curve here, which I showed you before. And so the idea is you have, again, some sort of oscillation, but there's this dissociation energy, at which point you would break this apart. And so it doesn't necessarily bounce back, but there's a sort of extra factor here that comes in to this internuclear separation. And so the Morse potential, it's a radial potential, looks something like this. And so it has, this is the overall potential energy at large distances, and then it has a functional form which looks like that. And so you can kind of think of it approximately as going as, well, this potential energy, and then you'll have some sort of oscillation here, which goes as the square of this radius, and then some extra constant. But it does have this exponential term, which is there. And so RE in this particular nomenclature is the minimum of the potential. So it's where this would, the minimum energy here in this internuclear separation. And then DE is the potential for this electron to just split off of the molecule. Okay, and so typically DE will be slightly different from D0, which is the ground state to the dissociation energy, which is a little bit strange, but nonetheless. So you can then think of the Schrodinger equation. If you were to solve this will give vibrational energies, which have a sort of energy. And this is now in terms of a sort of quantum number here. This thing is, you have a frequency of oscillation, and then you have, this is quantized. And this frequency of oscillation is related to our dissociation potential energy, the mass, and then this A here, this separation. Okay, and so then these are the vibrational quantum numbers. And so you have an electronic state, which is this, and then you have the vibrational states, which go like that. Then finally, you have the rotational states. And the rotational states, you have basically a sort of rotational Hamiltonian here, which goes as this orbital angular momentum, or rather, I guess the kinetic energy, the rotational kinetic energy, rather, not the Hamiltonian, goes as this moment of inertia and then the frequency. And we can think about the frequency as just this sort of angular momentum squared. And so we have a J value here. And so if we have a diatomic molecule, then the inertial, the moment of inertia is related to our mass of A and plus our mass of B times our radii squared. And so this thing approximately, you could sort of approximate it as this. So the total mass and the total radius squared. And so this thing is actually the reduced mass. So it's this product divided by the combination of the two. And so then we have this thing here, this J value is related to the moment of inertia and the frequency. And so then this gives us this sort of equality here. So the moment of inertia typically is a tensor. And so you have some appropriate value of this rotational frequency that you use. And so if you then plug this into Schrodinger's equation to find the energy levels, the energy levels, the rotational levels are a function of the angular momentum, which is quantized. And so you have J equals 0, 1, 2, which is the angular momentum quantum number. And this energy goes as not J squared, but J plus 1. And then you have your moment of inertia here. And So typically you can also express this in terms of a wave number. And so in terms of wave numbers, you would just divide this by the overall sort of energy constants here to give you a wave number. And so this thing, f of j, is going to be related again to j times j plus 1 and the moment of inertia, but you have an extra factor of 8 here. And so this thing, this quantity here, is known as b. And so b is related to the moment of inertia of your particular molecule times the quantum angular numbers. And so generally speaking, you will have energy levels which go like this. So you have j equals 0, 1, 2, 3, 4. And so these split by 2b, 4b, 6b, 8b. And so the difference between these things, if you look at the intensity of these things versus their energy, so you have 2b, 4b, 6b, 8b, you will have sort of separation of 2b between them, and you have sort of an intensity. And sorry, these are the total differences between these energy levels. If you think about it in terms of the frequency between one J level and the next, that frequency is related to the difference of these wave numbers here. And so that's equal to 2b times j plus 1. And so in general, you'll have that the spacing of these will be strongly proportional to 2b. Right, so if you look at, in the case of the dipole, going from j to j plus 1, the difference in energy here will be of the order of 2b times hc times j. Oops. And then if you have a quadruple case where you're going up to two values, then the difference in energy will be related to 2j minus 1. So the point here is that the transition energies are generally a linear function of j, and they're often separated by 2b times hc here. And so they have a very nice spacing that's uniform. Now, this is broken a little bit because you have centrifugal stretching as you have this rotation. So you have slight differences, which are a perturbation. And so they modify the energies a little bit. And so instead of just something which looks like this for the wave number, you have an extra second order term. And so typically the value of this thing is much less than the B term, which is related to the moment of inertia. And so this frequency then becomes something which looks like this, but then minus this extra factor here, where this is now going as j to the third. And so this again is a very, very small term, but nonetheless, you know, it will tweak things by a few %. And so you can get an idea of this from just a couple examples here. So B for the diatomic hydrogen, molecular hydrogen, and for CO, typically they have a nuclear separation of about 0.7 and 1.2 in particular. And then they have reduced masses about 8 times 10 to the minus 25 and 1 times 10 to the minus 23. And so we can calculate their moment of inertia, which are of the order of this and this. And so we can calculate B. And so B for the H2 is about 62, and for CO is about 2. And so if we think about CO and we look at the transition from 1 to 0, the frequency, this is going to be related to delta F of 1 to 0 times C here. And so generally you have, and this should be a constant, I think. Yeah, it's just a, okay, this is wave number, right? So we have to convert wave number from, where was it? Here, wave number to frequency. Right? So that's just C times this. Okay, so this frequency is going to be equal to 3b minus 2b, so you get 2b times the c, and so multiplying that out, you end up with a frequency of about 112. So this is very close to the actual observed frequency, where this frequency is now factoring in this. And so you can see that this is a very small, a few percent difference here from this factor of d. There are some other fine tunings that come into play that actually get you to this real value here, in addition to d. Questions? So you know, typically you can think of the spacing of these diatomic molecules as a ladder. And so you have J 1 to 0, 2 to 1, 3 to 2, and they go up uniformly in frequency. And so the frequency will go something like this. And so in terms of wave number, it might look like this in terms of the total intensity, where, you know, a temperature, if you have a material that's in some equilibrium temperature of 50 Kelvin, generally there are going to be certain transitions which are pumped and sort of excited. And so for 50 Kelvin, generally you'll have a peak around maybe sort of 15, a J transition of 15 to 14. And then if you increase the temperature, this J value will scale as the thermal temperature KT. And so you will then, you know, if you go from 50 to 1000, this is what a factor of, I guess, 26, something like that. So going from sort of somewhere in here, you end up scaling this. And so you have something which scales into wave numbers into the sort of hundreds here. In terms of the relative intensity, this is now in terms of frequency, you see something like that. And this is now in terms of 100 gigahertz or so. Okay, questions? All right. That's all nice. It turns out that you have coupling, and so rotators vibrate, rotations and vibrations are coupled. And so the constants that we previously defined turn out not to be constant. And so, in fact, this new value here of these values are a function of the original, which is of course related to the moment of inertia, but then also you have a correcting constant here, which is related to this wave number. So you can apply these corrections, and this is why we end up again you know, with something which is a little bit different. In principle, the d values also have some constant that you must apply, but generally you can kind of get away with just setting this as a constant because this is a perturbation on top of this. The vibrations typically will be of the order of this. So you have a, you know, similar to this wave number, you have a wave number here, which is related to the vibrations. And so here, these are constants, and you have some functional form, which is related to these wave numbers. So this then again, you have extra constants here as well. So it gets fairly complex. These things you can look up. They're tabulated from experiments done in, you know, vacuums and things like that. This is a sort of nice idea of what these vibrations do. And so each time I do it, it shows this thing. But this is sort of an asymmetric stretch. This is a symmetric stretch. This is a scissoring stretch for molecular hydrogen, sorry, or for water rather. Then you have carbon dioxide, and you have a sort of symmetric stretch and anti-symmetric stretch here. And then you have stretches which are potentially degenerate. So they have the same energy, but they have a different sort of functional form in terms of the exact energy, exactly which direction the vibration is oscillating in. And then you have more complex ones. This is methylene. And so this is a three-dimensional structure, whereas these are two-dimensional structures. So you don't have to worry about the third plane. In this one, you have to worry about the third plane. And so you can see these are coming in and out of the plane, vibrating like this. And then you can have couplings of all of these, right? And so you can have things that rotate around and do all sorts of things. So there's lots of flexibility with these molecules in terms of what vibrational states they can be. Okay, so we can then define the total energy here. And so the total energy is related to this sort of these wave numbers, this wave number, and then this total energy, modulo some issues with constants or units here. And so the point here is that you would define this total energy as the electronic state energy, the vibrational state energy, and the rotational state energy, right? And so these things obey selection rules. And so you have some set of rules which apply such that, for instance, you have a selection rule on the J values, and so they can typically only change by 0 or plus or minus 1, and you can't go from 0 to 0. And then you have a selection rule for the vibrational wave number. It can't go delta of 0. And so these vibrational rotational transitions are some of the most important and are dictated by these selection rules. And then finally, we can throw in the dipole moment. And so the dipole moment here, you can then potentially have dipole transitions, which are possible. And so, that's only if you have an asymmetric diatomic molecule, for instance, or a poly atomic molecule. If you have homonuclear molecules, there's no dipole moment. And so then you have to go to the quadrupole. And so you have quadrupole lines, which are delta J of plus or minus 2 that are allowed. So generally speaking, these transitions kind of occur in bunches. And so you have a bunch that will go from J to J plus 1. This is known as the R branch, and J to J minus 1, this is the P branch, and then J to J is the Q branch. And then for the quadrupole, you have the S branch and the O branch, which are in parallel to these. And so in general, remember that, okay, we had this rule where J can't go from 0 to 0. And so this means that typically there's no Q branch when you're in the ground state. And so this is a lot to take in, so it's a little bit easier, I think, to visualize. And so you have, this is sort of an upper level of a vibrational state, and here's a second vibrational state. You have a J value between them, whoops, and a J value between them. And so this is the 0 to 0 here, which was not allowed. And then you have the 1 to 0 that's allowed, the 2 to 1 that's allowed, 3 to 2 that's allowed, and so forth. Then you have the 3 to 4, for instance, that's allowed. And so these transitions, this frequency is related to the energy levels of these different states. And so this particular energy level is related to the electronic transition, and then the lower level transition, the upper level transition, and then this rotational factor as well. And this rotational factor goes as this. And so these are the different branches here. So what this actually looks like in terms of frequency is that you have some range of lines which are coupled around some frequency. And so this is the frequency for the 0-0 transition. And then you have the R branch, which goes to higher frequency. You have the P branch, which goes to lower frequency. And so in general, these will have a higher energy change, and these will have a lower energy change. And so frequency increases here as the J increases, and then frequency decreases as the J increases here. So these have higher energy, these have lower energy, right? So this is the idea behind all of this line emission structure. And so in general, this is what it would look like for CO. And so this is the transitions from the vibrational state to V to V-1 or to V-2. And so the CO for V1 to 0, the Q values end up being kind of here. This is 4 micron, so this is mid-infrared. And then you have the P values here and the R values going in this direction. And so this Q branch, these are the pure vibrational transitions. There's no change in J, right, for the Q branch here. And so all those lines are generally in the same position. And then you have the J to J-1. This is the R branch here. And so these are blueward of the Q lines. And then you have the P branch, which are redward. So higher energy, lower energy in terms of wavelength. Okay. And so you can measure these. You can then gauge various properties about CO from this. Typically, you have this can be even more complex. And so if you have a vibrating molecule, you can then, generally speaking, you have a band head. And so what happens is, as a function of, this is for the CO 2 to 0. So this is the quadrupole. And so here you have this transition, which then ends up summing up to this band head here, which is where all of the lines stop. And then actually you can have it go back a little bit. So it sums this way and gets smaller and smaller, and then it actually goes back again, which is denoted by the black versus the gray here. There's a better picture of it in the next slide. And so the idea here is that you have a rotational moment of inertia for the V equals 1, which is slightly larger than the V equals 0. And so the rotational energies for this level are slightly less than the V equals 0. And so the R branch, the blue branch, for high energy, the distance between the lines ends up decreasing with increasing J. And then eventually the lines will reach this minimum here, this band head, and then turn back around. And so this is, so that here basically what would happen is you go here, and then at some level they turn around, or something like that. This is for, I don't remember what molecule this is for, but this is just another example of these band heads. And so you can see sort of, this is the Q branch, which has a band head. This is the red branch, which has the R branch, which has a band head, and then the P branch as well. And so you can see this is the number, the J number, and this is the wavelength. So this is calculating via this, just to sort of show you some of the complexities here. The benefit is with one spectrum in the mid-infrared, for instance, you can measure all of these things, and that gets you a decent understanding of a large range of rotational states for a given vibrational state, if you have the resolution, spectral resolution to do it. Okay. This is the same version, but for H2. And so just showing, this is now the V to V-1 or the V to V-2. But note that the H2 has no dipole moment because it has equal molecules, right? And so again, you have the Q branch, you have the, now you have no R branch or no P branch, you just have the S branch and the O branch. And so this, is, again, you can measure this. This is in the K band here or in the mid-infrared. And so depending on the redshift and whatnot, you can partially measure this and get an estimate of some of the states of molecular hydrogen from the near-infrared spectrum. And again, it has similar things with band heads and whatnot, or potentially can. Okay, so the final thing, which is maybe coming to answer Janie's question, maybe not, is that you can go into the lab, you can measure spontaneous emission coefficients for all of these transitions, and so you can then calculate for a given line, you can calculate what the optical depth is, what the column density is for a given transition, what the you have an excitation temperature. And so generally speaking, if you have some radiation around, or if you have some population that's in equilibrium and some certain range of excited states, then there's a probability of a certain transition happening on a given time scale, which is related to it being in equilibrium. If it's not in equilibrium, then, well, these constants still work, but it becomes a little bit trickier problem. And so the idea here is you have a spontaneous emission coefficient from the upper to the lower level. You have some value of your statistical weights. You have the frequency, potentially with some width here, which is denoted in this integral here. And then you have a dependency, which is related to the temperature again. And so this will give you the number of atoms in the lower state. And so calculating all this out, you have something which looks like this, where we've assumed that this certain frequency can expand this exponential here, the Taylor expansion. So in general, this number will give you, this is the column density, and so this is related to the number density and the line of sight. So it's with some assumption about what's going on, the distribution of molecules along the line of sight, you can estimate what the number density is. But what the emission line is telling you from the depth of the absorption feature, or from the strength of the emission feature, is the column density. So this looks relatively simple. The only problem here is that there's a dependence on this excitation temperature. And this excitation temperature is a little weird because it is not the real temperature. It's what this excitation temperature is measuring here is the ratio of the upper to lower levels of this particular sort of two-level system. So this excitation temperature is determined by a balance of radiative and collision excitations and de-excitations. So it is somewhat dependent on where this thing is, and kind of harkens back to the last plot I showed from the last lecture, or the start of this lecture, which showed the range between collisionally and collisionally dominated and radiatively dominated systems. Right? And so that sort of uncertainty gives you a little bit of uncertainty about the excitation temperature. You can, in some situations, the excitation temperature can get you the actual temperature. And so this excitation temperature, as I mentioned, it can take on a wide range of values here. But if you assume LTE, local thermodynamic equilibrium, sometimes you can solve for this. And particularly you can solve when the optical depth is low. And the reason you can do this is that this, let's say, basically you have that this column density is equal to this times this integral. And this thing here, when it's a low optical depth, is equal to the maximal Boltzmann temperature. And so you can combine these two, and you can estimate this as being the brightness temperature, and you can then kind of estimate what the column density is in terms of its brightness temperature. So what this allows you to do is get rid of the excitation temperature. And so then you can sort of estimate something about the system. And so generally speaking here, if the line is optically thin, in the optically thin regime, then what happens is this column density, you just estimate it over the average telescope beam, you get a brightness temperature based on that. And so you can just use radiative transfer to, you estimate this as a function of frequency, and this thing is going to be related to the excitation temperature and tau in this functional form. Okay, so this allows you to sort of piece together things, but typically you have to, if you don't have a good handle on all of this, you have to, if you have something that's in an optically thick regime, then it becomes very difficult to pull out how to convert the line here into how should I say, into a total value of say the number density of the material, because it then becomes quite complex. And so you can kind of think of it as, if you have something that's optically thick, what you're seeing is the shell at the, the skin of this cloud, right, at the edge of the cloud. And so inside of that, when it's optically thick, you're not really able to measure that. And so you don't have a handle on what's going on inside. Whereas if it's optically thin, then you can see all the way through it, and this gives you a handle on what the number density or column density can be. Okay, one final thing here, we'll talk a little bit more about this tomorrow, but one final thing is just to mention that you can have the Stark and Zeeman effects that come into play. So if you have an electric field or a magnetic field, these will do level splittings, and so these will change the relative wavelengths, and so you will, if there's a electric or dipole moment associated with the molecule, which there very well could be if it's not diatomic, then the levels will split depending on the orientation with respect to the field. And so in general, the Zeeman effect is super useful for studying atomic and paramagnetic molecules. And the Stark effect is useful for studying top symmetric molecules. And so water or hydrogen dioxide, ammonium, etc. That's just an example of this line splitting. Okay. So Jenny, coming back to your question, did I try to answer it? Do you still have that question?
Yeah, I think that I was a bit confused with the meaning of the electronic transition and the other, but I have still a doubt. So it's possible that a molecule has these, yeah.
Si quieres preguntar en español, está bien.
No. I'm also confusing both.
Sí,
Yeah,
no puedes alcanzar las palabras.
Yeah, no, but so a molecule could have a vibrational rotational state, but I don't understand if the same molecule can also have the electronic state. I don't know if.
Yes, so the molecules will have all of those.
Okay.
Depending on what the field, where it is, what it's doing. Right. So in general, the electronic states have a really high energy, and so it may be the case that you're always in the ground state because you're not in a photon field that's got UV photon field that'll excite the electronic states, or you don't have enough electron energy. If you're in a gas cloud that's got 50 Kelvin or 30 Kelvin, right, you're never really going to excite the electronic states. You're mostly going to be living down here. And in fact, you may not even have enough energy to excite the vibrational states. And so you may be sitting in the center of a molecular cloud, you may be sitting only in the ground state with very little vibrational states, and you're just talking about rotational states, right? Which is what people observe in the radio. And then for more excited states, then there's the possibility of having the vibrational states, which we saw in the near infrared, and the vibrational states, you have a coupling between the vibration and rotation, which leads to a crap ton of lines because small changes in the vibrational energy will be able to excite internally different vibrational states, and so you get this where the hell were the band head things, right? You get this whole sort of regime of possible emission lines, and so again, there are certain physical situations which will lead to this, and you can use the observations of these for this particular vibrational state. And if you don't have enough resolution, what you end up seeing is just blurring all of this. But potentially there's a lot of information here about what that particular molecule is experiencing, or what, if you assume there's a gas of it's an LTE, then what that gas is experiencing, right? Which you can probe via this. But it's not super trivial because in general, right, we only have spectrographs that go up to about 2.4 micron. And so we only measure the S states, and then we have to make some assumptions, but we can say, hey, we have the hydrogen, we can use those emission lines or the absorption lines to estimate what the line of sight hydrogen is under some assumptions, or if it's an emission, what the gas is doing is giving rise to these emission lines. Does that make sense? But then there's the potential to have electronic transitions, which can happen even in the ISM because there's a photon field of UV photons that is just around. And so you will be able to, and certainly there are hydrogen molecules that are in the ISM, and there's UV light from a quasar, for instance, passing through it. And there's the possibility that the UV light will excite the hydrogen molecule into the higher electronic state, leave an absorption feature, right? And then the line is emitted in some other direction. And so if you look at the spectrum of a quasar, for instance, you'll see the absorption features from the electronic transitions from this molecule. And it's a way of probing molecular hydrogen along the line of sight, for instance. Yeah, does it?
Yeah, now it's more clear. Yeah.
And these are all dictated, to some extent by the same things we were talking about with atomic species, where you have a spontaneous emission coefficient, which will, tells you how frequent the line is going to have a radiative decay, and then you have a rate equation which you would plug in, which would say, okay, there's that transition which will happen, and then we have the electrons which are coming around, or the photon field which is there, and in certain situations, if we're collisionally dominated or photon dominated, we can kind of calculate something from that rate equation. If it's a mix, then it becomes complicated. So you can play similar games as you would with the atomic things that we were doing with photonization, for instance. But the only problem is that you just have to be very careful about what's going on here, because you can be fooled by, and we'll see this next time on Monday. You can be fooled if you only have a few transitions. You don't necessarily know what you're looking at. Other questions?
When we talked about the molecular structure, we could relate that in some way with the Clebsch-Jordan coefficients.
The what coefficients?
Clebsch-Jordan coefficients, when we couple angular momentums.
You've gone beyond my knowledge of molecular physics. Yeah, I don't know what those coefficients are necessarily. But yeah, I mean, maybe that's a, yeah, I'd have to look up what that is exactly.
Okay, thank you. Yeah, it's no, just a question.
Yeah, all of this pushes very rapidly into chemistry, and so I stopped taking chemistry in high school.
Okay, thank you.
But if you know, there's the astrochemistry course with Viviana. She will get into some of this. So, okay, other questions, thoughts? So let's see.
I have another question, but more regarding to the homework. I don't know if the Einstein coefficient is a value that is measured. It's tabulated for some. Yeah, some lines.
You can look the transition probabilities up.
Oh, okay. Thank you.
Okay, and then to answer Carlos's question about homework number 11, no.
Oh.
Sorry.
No,
it was mostly just that I didn't want to make homework 10 too long, and originally homework 10 had molecular problems in it, and we hadn't gotten there yet. So that was why I wanted to. It will be shorter though. It's only going to be 2 questions. So I wanted to have a little bit of a taste of what one can do. And they won't, I don't think they'll be too hard. No. Okay. Anything else? Okay. And then I will talk to you guys. Oh, and think about when you want to take the test, the exam 2. And the format of exam 2 will be very similar to the format of exam 1. So there'll be less doubts, I hope. Okay. All right. Take care, everyone. Have a good rest of your week.